Good morning. Now we're going to move a little farther south to the U.S. Western mountains and really try to answer the question, how much is snowmelt contributing to flooding during rain-on-snow events compared to rainfall? And I'd like to acknowledge my co-authors, Jessica Lundquist and Martin Clark. So during the largest floods over the West Coast, we typically have caused by atmospheric rivers. And these also bring a lot of precipitation, but a high snow level. So we have a larger area contributing to runoff over a basin. And we also have a larger area of the snowpack that can be exposed to warm, windy atmosphere that can drive potentially high melt rates. However, the observations that we have available aren't everywhere we want them to be in a basin to be able to calculate a total basin contribution from snowmelt versus rainfall. There have been many case studies that have found a range of contribution from snowmelt during these events, from 4 to 72%. But it's more difficult because of the spatial variability within a basin and the elevations that we have these stations at to calculate the total contribution from snowmelt versus rainfall. So we decided to take a idealized modeling approach to estimate how much rainfall, snowmelt is contributing during these storms by looking at the combination of how the snow level timing, hypsometry, and vegetation controls the snowmelt contribution. We decided to focus on 3 basins along the West Coast, one up in the Snoqualmie Basin in the Central Cascades, one in central Sierra Nevada and southern Sierra Nevada. And these basins span a latitude range, so they see different frequency of atmospheric river events, and they also have a different basin hypsometry, which can be important and we'll come back to later. We use the distributed hydrology, soil, and vegetation model to do our simulations. And its energy balance model has a 2-layer pack. It uses an Anderson stability correction for the turbulent heat flux calculations. So to be able to represent our basin in this idealized manner and be able to separate these different controls, we first, for each basin, divided up into elevation bins and had 2 simulations, one with a forest vegetation and one with a grass vegetation. We then can use the true observed fraction of vegetation in each elevation bin to calculate the fraction from each of those simulations for that elevation bin. And then using the observed area at each elevation bin, we can come up with the total volume of snowmelt and rainfall contributed at that elevation bin. So here we're not including runoff processes, whether we have frozen soil or saturated, but just focusing on the contribution of water available for runoff. We need forcing data for our simulation, so because we wanted a large period and similar forcing data over all of our basins, we used the Maurer 2002 12-kilometer data set. And we use this data set mainly because it's been well used in the literature. And we note that there are some deficiencies with this data set, which I'll address later in the talk. So for each of these basins, the 12-kilometer grid cells were binned into elevation bins and used to drive our simulations of the rain-on-snow events. I'm going to focus on an example storm that's been well studied in literature and actually ended up contributing the most snowmelt of all of the basins and storms we examined. This caused widespread damage on the Feather River Basin and the central Sierra Nevadas. So these are simulated results for the storm showing for elevation and time, the change in SWE. So the blue colors are indicating we have snowfall above the snow level, and the red are showing melting snow. And we can compare those rates with the rainfall amounts that are occurring below the snow level, and we see that they have comparable snowmelt and rainfall rates. And then using the correct area for each elevation bin, we can calculate the total input to the basin from both snowmelt and rainfall. And so over the peak 3-day period, we can calculate the contribution from snowmelt for the storm was 23%. So we also looked at the impact of vegetation on controlling the energy available for snowmelt. So this is showing for that same storm, the thin line is showing the initial available SWE before the storm, so the antecedent conditions, and then the thick line is the total snowmelt that occurred. So above that horizontal line, we're in an energy limited regime, and below it, we're in a mass limited. And if we compare the simulated energy balance components during that storm, the sensible and latent heat flux dominated because we're in a clearing at this location. And we can compare that with our simulation in a total forest canopy, which we have a reduction in the wind speed from the forest and turbulent heat fluxes. What's interesting is we have a shift down to lower elevations with the forest being added. And this can be important when we have non-uniform area-shaped basins. We have that when that coincident maximum elevation of maximum melt coincides with the largest area, then we can generate the largest input from snowmelt. So this is an example here where we have, for a uniform area, the contributions from rainfall and snowmelt. And then looking at the East North Fork Feather River Basin here in Sierra Nevada, which has a large area at mid elevations. And you can see how that has a simple impact on the rainfall and snowmelt contributions. So to be able to quantify over a large range of storms, we looked at the top 10 largest 3-day total precipitation amounts between 1980 and 2008. And if we just look at our simulations with a uniform area under a grass vegetation, we see that there is a large range between each basin, indicating the type of how much antecedent snow was available and the range of the snow level during the storm. When we go to a forest vegetation, this cuts down the contribution from snowmelt in all basins. And when we use the actual real fraction of vegetation within that basin for the Snoqualmie and East North Fork Feather River Basin in blue and red, we see a little higher fraction because there's been some logging in these basins, and we have a higher fraction of grass or clearing in these basins. You can also look at the impact of the hypsometry on the snowmelt contribution by looking from uniform to the real area basin. And we see a different impact for the Snoqualmie Basin in blue, where we have a reduction in the importance of snowmelt. But for the East North Fork River Basin, we have an increase because more often we have that coincident area of maximum snowmelt with the largest area elevation. And finally, using the real area and the real vegetation fraction, we're able to calculate the total contribution. Our best estimate of this during these storms that ranged from 0 to 23%, but there were, so you can see some large differences between each basin, depending on these 3 controls. Finally, as I mentioned, there is some uncertainty in the meteorological forcing data that we used. So we tried to estimate some uncertainty bounds on these forcing and looked for this 1997 storm, how that impacts our simulation. The thin lines are showing the variability in the initial conditions of SWE, and then the thick lines, the total snowmelt that occurred during that event. And if we just look at the change in snowmelt, we can see some differences up to 50 millimeters of lost SWE. But what's interesting is the compensation that occurs if you have, say, the green line showing an increased wind speed of 2 meters per second. At the lower elevations, we have less snow available prior to that storm, where at the higher elevations, we have more energy to melt based on that mass-limited and energy-limited regimes. So we did this for all the storms and study basins and kind of capped our uncertainty at this maximum contribution, about plus or minus 3%. So to conclude, we found the historical snowmelt contribution for these three basins over our study period between 0 and 23%, plus or minus 3%, and that the elevation of maximum snowmelt, when that coincided with the largest elevation, can be very important. And that's interesting in the context of a potentially rising snow level in the future, and how this may shift to larger, depending on the basin hypsometry. I finally make a plug for a poster I have this afternoon that will be looking more in detail at simulating internal pack conditions during rain on snow events to look at on some processes that we have glossed over in this study. So thank you. I can take questions.
Thanks, Nick. We have time for a couple of questions. Keith?
That was a great talk. One question I had is how do you define snowmelt as an output from the model? Is this water exiting the snowpack, or is it actually just a cue that you're calculating the energy balance?
It is the model calculated snowmelt. So it's leaving the snowpack, but not including runoff processes. So it's not taking into account if there's saturated soils below the snowpack or it's frozen or not.